Hello again. We are going to talk about recursive sequences or recurrence relations for the next few videos while we complete out this chapter. So we're going to talk about, first of all, what recursive sequences are and what they look like. So there are ways to define them. First, we can use deductive rules, and they allow you to define the nth term just by using n, not using any terms that come before it. And we'll talk about that in the next slide. So for example, I can say that the nth term is n cubed plus 2n. So, the first term would be 1 cubed plus 2 times 1. The second term would be 2 cubed plus 2 times 2, and so on. Okay, so that's actually a really nice way to write a sequence, but we don't always get the sequence in that form. So if I actually do plug in n equals 1, n equals 2, and so on, I get the sequence 3, 12, 33, 72, and 135. And there are obviously more terms after that. Okay, so that is the deductive rules. Then we have recursive definitions, and those are the ones that each term is defined by the terms that come before it in the same sequence. So for example, I've written that the nth term is equal to 2 times the n minus first term, and then we subtract the n minus second term. So every term is 2 times the term that comes before it, and then we subtract the term that comes 2 before that. And obviously to do this, we would need actually the first 2 terms in the sequence defined for us. All right, so let's suppose that we have the first term being 1 and the second term being 3, and then we'll calculate the next 3 terms. Okay, so the third term will be 2 times the second term minus the first term. Well, the second term was 3, the first term was 1, so I get 2 times 3 minus 1, and that's 5. So I now know the third term is 5. The fourth term would then be 2 times the third term minus the second term, and if I plug those in, which I both know, that's 2 times 5 minus 3, and that's 7. And finally, the fifth term is going to be 2 times the fourth term minus the third term. I just calculated the fourth term, that's 7. I remember that the third term was 5, so I get 2 times 7 minus 5, and that's 9. Okay, so let's look at that sequence again. It went 1, 3, 5, 7, 9. Well, that's a pattern I already know. So I could write it as the nth term is equal to 2 times n minus 1, meaning that the first term is 2 times 1 minus 1. The second term is 2 times 2 minus 1, and so on, and I would get the exact same sequence. So that's my guess as to what the rule is, and it's a pretty good guess. So I'm going to prove this using proof by strong induction, which is what we talked about in the last video. So these are, just to remind you, the 3 steps that we will do. We will prove it true for the initial terms, and remember we have 2 of them. We will assume it true for n less than some arbitrary value k, and then we will prove it true for n equals k. So let's do this. All right, so here's how the problem would be stated. A sequence is defined by the recurrence relation that we started with. The nth term is equal to twice the n minus first term minus the n minus second term. We've got the first term being 1, the second term being 3, and we are going to prove by induction that the nth term is actually 2 times n minus 1. So we're going to prove it true for n equals 1 and n equals 2. So using the 2n minus 1 expression, if I replace n with 1, I get that 2 times 1 minus 1 is 1, and that's true. The first term was actually 1. The second term is 2 times 2 minus 1, which is 3, and that's actually true as well, based on the given information. Now what I'm going to do in the second step is assume that the nth term is 2n minus 1 for all n's that are less than k. So n equaling k minus 1, n equaling k minus 2, and all the way down the line to anything that's less than k. Okay, so that's step 2 specifically, and those are the ones that I mentioned. The k minus first term is going to be written as 2 times k minus 1 minus 1, and the k minus second term is going to be 2 times k minus 2 minus 1. We're going to assume those are true, and then prove for n equals k. That's the hard part. All right, so we're going to prove that the kth term is actually 2 times k minus 1 based on the assumptions that I did in step 2. So I start with the recursive definition. This is what I was given. The kth term is 2 times the k minus first term minus the k minus second term. So in step 2, I made those assumptions and I kept them in blue and purple so that you could see where I'm placing, where I'm doing my replacements. Okay, I make those substitutions. And so the kth term is now 2 times k minus 1 minus 2 times k minus 2 minus 1. Now this is just a big algebraic expression that I need to simplify. So I simplify the parentheses first, and that blue stuff in the first set of parentheses becomes 2k minus 3, and the purple stuff in the second set of parentheses becomes 2k minus 5. If I expand the parentheses or distribute the numbers in front of the parentheses into the parentheses, I get 4k minus 6 equals, 4k minus 6 minus 2k plus 5, and that is 2k minus 1. And that's what I was required to show. If you look at the very top of the screen, that's what I was required to show. So I'm actually done, and I've proven that the nth term of this sequence is actually 2n minus 1. So that is kind of an introduction to recursive sequences and trying to guess at what the pattern is using a definition that has n in it instead of defining it by the terms that come before. So if you have any questions, please let me know, and I will see you tomorrow.